Hey, we're in chapter 2. Woohoo! We're going to talk about categorical data displays. So for categorical data displays, basically what you're going to have is a count of the number of items that fall into different categories. Our example is going to be college students. And the category is what college is your major? And then we're going to count how many students are in each of the colleges. And we're going to draw a graph of that. Okay, so here's the number of students. 586 in STEM, 1422 in CHAS, 1120 in HSB, 875 in KEEPS. They keep changing the names, so those may no longer make sense, but that's what I'm using. And then we make, these are the frequencies. We'll make a bar graph of the frequency. So above each of the names here, in whatever order you like, there's no natural order to colleges, we make a bar whose height is the count. So above the bar here, it's going to be 586. So this bar is 586 tall. And this one is 1422 tall, 1120, 875. And so the key features of a bar graph of frequencies is the bars don't touch ordinarily, because that's to distinguish this type of graph from other types of graphs where the bars do touch. Ordinarily, they would start at 0. So where this crosses down here is 0. And the reason for that is you want the area proportional to count. So if you start at 0, then the height is the count. The height times width is area. If the widths are all the same, so we want that. The widths are the same. So if the widths are the same and the heights are the count, then the areas are proportional to the counts, or to the, you could call that the frequencies. To the frequency count, same thing. So there it is. You can easily see by eye who's tall, who's short. You can see who's twice as big as who. So this 586 is just about half of 1120. If I drew it right, that would look to be about half of that. And this is more than twice as big, because 1422 is more than twice 586. And you can tell by the area there, it's more than twice that area. So your eye does a pretty good job of assessing the counts, because count and area match up. Double the area, double the count. That's what you'd like to know. Now, it's sometimes a little hard to compare heights of bars. If you have lots of bars, if they're approximately the same height and they're not next to each other, a way to accommodate that is to make what's called a Pareto graph. And what you do there is you put the bars next in increasing or decreasing order. So that makes bars that are about the same size next to each other. And then it's easy to tell which ones, well, you know, because they're getting bigger this way as well, that one's bigger than that, even though they're about the same size. So that lets you quickly determine who's bigger than who if you cared, even if they're close to the same size. Here, you might not be able to see right away, or these things are about the same size, who goes where. So if you arrange them in increasing order or decreasing order, you can tell. So that would be the same bars, just swapped around in different orders. So that's a Pareto graph. Okay, and then we can also make relative frequency graphs. They mark the y-axis in fraction of the whole. Here's the relative frequencies here. So we figured out the total of these 4 values. So there are 4,003 students overall. So if I know 586 are STEM students, then 586 divided by 4,003, which is 0.146, is the fraction of the students that are STEM students. Here's all the fractions. Those fractions should add up to be 1. And then we could then relabel this axis with fractions. So 2,000 becomes just about 1/2. And so these fractions then, and the heights of STEM, 0.146 would be right in here, 0.146. And then for KEEPS is 219. 219 right in here, and so on. Or we could use that same scheme here and label this axis with relative frequencies, or fractions of the whole, and just replace 2,000 with just about 1/2, and relabel the axis. And then you'll have a relative frequency graph. So you have regular relative frequency graphs and Pareto relative frequency graphs, depending on whether you've stacked the bars in order or not. And then, as a third type of graph, or maybe fourth if we think about this, frequency, relative frequency, frequency, relative frequency, Pareto and not Pareto, that's 4 kinds of graphs. We could also make a pie chart. A pie chart A pie chart divides a disk into pie slices whose areas are proportional to the counts. Okay. So that would mean, say, this area here for stem. Area is proportional to central angle. So twice the central angle, twice the area. So if we take the total angle as 360 degrees and take what fraction of the whole it is, 0.146, take 360 times 0.146, I get 52.6. That'll be this angle here, if you want to try to draw it. So I didn't do a very good job, I just did it by eye. So this angle here should be 52.6 degrees, like that. And then for Chaz, it's 35% of the whole, 35% of 360, which is once around 127 degrees. So down here, that should be 127.6 degrees. So it's pretty easy once you have the relative frequencies to create pie charts measuring off angles whose size is 360 degrees times that relative frequency, and that gives you a way to draw the pie chart. Of course, we have computers that do all this stuff automatically. So that's not a challenge, but it would be a challenge if you were asked to say what the angle is here, which might happen someday. What the HSB angle should be. 28% of 360 degrees goes there. It says for pie charts, it's not as easy to compare counts as with a Pareto graph. So you might have slices that are almost the same size. And sometimes pie charts have lots of slices. It's not very fun to look at. And it's pretty hard to tell who's who. So if you're trying to compare sizes and there are lots of components or lots of categories, then probably you're better off with a Pareto graph. If there's more than 4 categories, you're going to run into things that look approximately the same that aren't next to each other either way. And a Pareto graph is going to help you do that. So that's the first set of categorical data displays. Now this particular kind of data is important because what we're thinking we have here is parts of a whole. That's to say, each student is only in one category. Right, so when we're dividing up the whole into these pieces where you can't be in more than one piece at a time, where the categories don't overlap, we might say they're disjoint. You can't be in 2 at once. Then we can make a pie graph. Otherwise we can't do it because you're just lying otherwise. So here, as you make these pie slices, when you see pie slices like that and you have their name like this, you're assuming they don't overlap. There's no way that one crosses over the other like this. You're not allowing that to happen. So it has to be parts of a whole. So this particular example is parts of a whole. And plus, if you're doing relative frequencies, you also need parts of a whole, because why would you divide this by the total if it's not that fraction of the total? So here we have parts of a whole. Relative frequency only works with parts of a whole. It doesn't make sense to say that one group has a relative frequency of 50% if half of the individuals don't belong to that category. So if the totals don't add up to be 100%, then talking about relative frequency doesn't make a lot of sense. You can still talk about frequencies that have got this many of this many of that, even though you can be in 2 categories. You know, this here could be, what can we put down here where you might be in one or the other? I guess you could have, you have a cell phone, you have a tablet, you have a laptop, you have internet access at home. We could have counts for how many students have all those things, and you can have more than one, and the counts make sense. But you wouldn't make a relative frequency graph, and you wouldn't make a pie chart of that information. So we'll see some of that coming up in a second, where we'll have to decide, is the information parts of a whole, so relative frequency makes sense, and pie charts make sense, or is it not parts of a whole, in which case all you really have is frequency graphs you can look at. And here we go.